This video explores a 350-year quest for a lost formula and how a 20-year-old genius solved an equation that had baffled mathematicians for centuries. The first key was the quadratic formula. For equations of the form ax squared plus bx plus c equals 0, this universal formula unlocks the solution using simple arithmetic operations and taking roots. Mathematicians sought to extend this success to higher-degree polynomials. Formulas for cubic and quartic polynomials were eventually discovered, though they were vastly more complex. The quest seemed to be on the right track. However, the pattern breaks at degree 5. There is no general formula for the quintic polynomial built from the usual arithmetic operations and taking nth roots. Every quintic polynomial has 5 roots, but we cannot write them down using a neat, universal formula. The question was how to prove such a negative statement. You cannot simply test every potential formula. For over 350 years, this puzzle baffled mathematical minds, requiring a completely new perspective. In 1830, the puzzle was cracked by Évariste Galois, a 20-year-old French mathematician. On the eve of a fatal duel, he laid out a revolutionary theory that redefined algebra and solved the quintic problem. Galois' breakthrough was to shift the focus from finding a formula to studying the symmetries of the roots themselves. The problem wasn't one of calculation, but of structure, the Galois insight, symmetry. Galois associated every polynomial with an object called a group, a collection of its symmetries. The Galois group consists of all the ways you can permute the roots without changing the relationships between them. Galois proved a polynomial is solvable by radicals, if and only if its Galois group has a special property. It must be solvable, meaning it can be broken down into simpler pieces called a cyclic tower. If the structure is simple enough, a formula exists. The Galois group of a quadratic has 2 symmetries, swapping the 2 roots. This simple back-and-forth structure is solvable. A cubic's group has 6 symmetries, which is also solvable, containing subgroups corresponding to roots. For the general quintic, the Galois group is S5, the group of all 120 permutations. Crucially, it contains a subgroup, A5, which is simple. This structural rigidity is the fundamental barrier. The quintic's symmetry is too intricate for a step-by-step process of radicals. The story does not end with impossibility. While no formula using radicals exists, the quintic solutions can be expressed using advanced tools like elliptic modular functions, designed to encode the complex symmetries of the group A5. Galois' quest accidentally gave birth to group theory, one of modern science's most powerful concepts. The study of symmetry is now a fundamental tool everywhere, from mathematics and physics to chemistry and modern cryptography. The ultimate insight is that the story of the quintic is remarkable, not just because it couldn't be solved by radicals, but because it revealed that the structure of equations is often more important than the solutions themselves.